we wanted to have geometric regions as first-class citizens. One of the driving applications was, in fact, finite element analysis, to be able to solve partial differential equations over regions. You know, and a region might be an engine block, it might be a country, it might be the shape of a letter, all kinds of things. So we want that level of flexibility. And I wanted to show you some of the things. I'll talk more about sort of the premise around it, but I want to kind of get going with the things. And so part of what we have is that we've generalized a lot of high-level solvers to work over regions. That goes for integration, solving differential equations. That goes for optimizations. You can optimize over regions and equations and so on. And so let's look at a little bit of that to get a sense of it. So this is not a fake example. This actually works, the one that you see there on top. And who doesn't need to do that? Right. So one of the things that you can do is to, and so I'm going to introduce regions without introducing regions, but talk about how you can use them. So we can do plot over regions. So in this case, we can see that we use what you used. If you used to Mathematica, these are graphics primitives. Almost all graphics primitives are also geometric primitives, but they need to have a clear-cut geometric meaning of what's in the point set for that to be the case. But in reality, we've actually also effectively doubled the number of new primitives that are also geometric regions and graphic primitives. So there are now things like a simplex, for instance. There are new primitives like ellipsoids in any orientation, and so on. So we'll see some of that in a second. Did it actually evaluate? Okay. Is this a really wimpy processor, John?
It's a 2012 MacBook Air.
Oh, that's good enough. Okay. And that works for a variety of these plot functions. So you can plot over regions. It needs to be, in this case, a two-dimensional region. We can integrate over a region, and so works just the same way in any number of dimensions. So it's not restricted. Our geometry is not restricted to 2D and 3D. That's what we're most used to. But 1D geometry is perfectly fine, and 4D and 50D geometry is also fine. If we do that, I'm just sorry, I see that the output is there, but I just want to make sure that we're running okay. So when we give such a region here, if it's we can see that we can have parameters in a region or a function, in which case the result also will have parameters. So you see how it depends on the radius, for instance, in this case. Numerical operations, of course, cannot have parameters in them, but it works, should work the very same way, just as, okay, this scroller works the wrong way. Did you tune that? You're scrolling? It's the opposite way.
Yes.
Okay.
The way it was 20 years before Apple changed it.
Right. Okay. Okay. So so we can integrate any function, and a polygon is a perfectly good one, and in this case, it's still full dimensional, and you can see we can use the fact that we could visualize over them. And here's an example of integrating in higher dimension. This is a ball. So many of our graphics primitives that are also geometry primitives have been generalized. So a ball, for instance, can be a ball in any number of dimensions. And you can see that we can get a result out for that. We can also do that numerically. Another interesting thing about integration is that what happens if I give it a curve, like a circle? Can I integrate over a circle as opposed to a disk? So disk is 2D, but I have two variables. So the answer is yes, and it will change the measure, so it in fact performs a curve integral in this case. It correctly changed the integration measure. And so if I integrate one, over that circle, it should give me the measure of it, otherwise known as the length, or the arc length. And we all recognize this formula, hopefully. Works, numerically as well, and here's the same thing with a line and so on. Okay. So, next up, we can solve partial differential equations. Now, partial differential equations is not a typical high school topic, but I think it can be. at some point. But the point is that it's no harder than the examples that you've seen up to this point that we solve over a region. So you can see that I've been using this idiom here. I use the element, I have my variables are in a region. It's probably felt so natural you didn't even think about it. But we can do the same. So in this case, I have a Poisson equation with Laplacian equal to 1, and then I set the boundary condition, the value along the boundary here, following a sinusoid. And of course, there's a lot of automation that goes into it. And this is what Oliver Rubenkoenig will be talking about tomorrow a great deal, exactly how that works. We can then plot our solution over that. We can optimize over a region. So once you learn this idiom of saying x, y, z in region, you can see that it's going to be working across the system in a variety of ways. So let's say I have a region that's a disk, another one that's a rectangle. I can find what is the minimum distance between points where P1 is in the disk and P2 is in the rectangle. Okay, and I get the minimizing argument for that, which is the 2 points. And here I'm using another thing that if you're a connoisseur of Mathematica, you know that we haven't really used vector variables particularly. And so this uses a symbolic vector variable as well. Or I can do the dual problem of find the maximal distance. So now I'm going to get the nearest and farthest points. So let's just use those values. And you can see underneath here, I just used the resulting values to do this illustration. What about solving equations? So we can use, you can use these kinds of region element statements, mixed in with equations, inequalities, and so on. And so let's just do a simple example here. So I have a line, an infinite line, and a circle, and I want the points that are on the line and on the circle at the same time. And we solve that, and now I'm using an exact solver, and it needs the definition of what the line and circle are. Apart from that, it should work. And again, I just used that solution, to create that visualization. So I think that this is something that you will probably have to solve in high school at some point or another. This works for any of them. So if I used nsolve and we can go look at the documentation, you'll find lots of examples along these lines. And we can go crazy, it's once you have an easy way to formulate things, it's not very hard to push things, a curve and a surface and, many surfaces. Just keep going, it's once you have a good language and it sort of works. Now, how do I get back?
Just close it, Command W.
Thank you. All right, so that's solvers. Okay, all in all, there are, I think, about 28 of these solvers in Mathematica that have been upgraded and understands geometric regions and can do something quite sensible with them. Okay. Oh yeah, this one was a little bigger. So now, for regions, there's a number of standard properties that we need to know about regions, and I'm going to browse over this a little fast. I have no idea what I'm doing on time. So one thing that you often need to do on regions is, every region that we have in Mathematica is embedded in some dimension. It lives in 3D. It lives in 2D. But you can have a curve in 3D. So its geometric dimension is 1, but its embedding dimension is 3. A lot of things get triggered on that. That determines the integration measure to use, for instance. So Other important thing, we've already seen element being used a great deal to express, to assert that a point is in a region, but we also need to have point in polygon tests, point in region tests. And so there's something like that. So normally, just like with the function nearest in Mathematica, if you just call it on a region, you will get a function that you can execute repeatedly. You know, you're going to do tens of thousands of these calls. So element means asserting, and we can use it to integrate. If we ask for member and we use variables, we'll actually get the symbolic formulas for it. Or if I did the same example here, but okay. So this one, the element function wants what we call a constant region, one that doesn't have parameters in it. So then you get what's called a region member function that you can just apply to points repeatedly. You might need to do this, as I said, tens of thousands or hundreds of thousands of times. Now, I call these moment properties. So measure is the generalization of arc length, area, and volume. So we have those functions too. And so here is the sort of picture of, for a curve, we call it length. For an area, we call it, for a 2D region, we call it area, and for 3D, we call it volume. And also, that generalizes to zero-dimensional regions, in which case the measure is known as count. But it generalizes higher too. So then, so the first thing that just works is to get sort of what's the, things like this, like what's the measure, in this case, the length of an ellipse, where the semi-axis lengths are R1 and R2. Or similarly for a filled ellipse, and so on. So some of these come out simple and they work typically in any number of dimensions. And so why did I call that a moment? Because they're really defined as an integral, as we saw. So the actual definition of measure is sort of integration over the region of 1. We're going to look at the next thing, which is to measure the center of a region, which is that we integrate sort of basically the first moment, but we're going to normalize by the measure of it. So m is the measure. And that gives us a sense of center for, it's also known as center of gravity in mechanics, or center of mass. And the next one up, if you want a quadratic moment, that would be inertia. So here is, for instance, as we would expect for some of these simple regions. Okay. The other thing, so moment properties, they're sort of integration or integral related properties. The other one are sort of distance properties or optimization properties. So one thing is to get the nearest point to a region. So given a point and a region, find the nearest point in the region to that point. And once you find a point, you can trivially find its distance. And there's something called a sign distance, where if you have a point inside the region, the distance is negative. It's the distance to the complement of the region, which is kind of useful for many things. So here are some examples. It just has a big illustration, that's all. It's just... How much memory does this thing have? I mean, it does look like a toy, I'm just saying, you know.
So it can calculate the nearest distance between an n-dimensional object and an m-dimensional object?
Yes, if they're both embedded in the same dimension space. So anyways, these are examples of iso-distance curves here. So I have a disk as my region, and all the points on the red curve here are at the same minimum distance from the region. Okay? So in fact, this is a good way to create new geometric regions by creating something that are a certain distance away from an existing one. And these are similarly, you know, so these are iso-distances away. These ones are 0.3 away from a standard rectangle, and similarly for these 3D ones. So this one, of course, had to compute many distances in order to make a nice curve, surface of it. You know, most of these distance formulas are very complicated. I'll see if I'll show some here, okay? So let's do nearest instead. So this is an illustration that's just trying to say, for each point here, what is the corresponding nearest point? So I'm drawing a little line from it. And so you can see that for most convex objects, it's kind of easy to guess, or somewhat easy to guess what it's going to be. For non-convex objects, it gets a little crazier. And so what am I doing? Oh, I'm just taking a polygon. Okay. And sort of computing the nearest point as I move it along. And you can see when you have these non-convex parts of it, it gets very sort of non-local in nature. These get very complicated, but we can give actually analytic forms for surprisingly many. You can compute them for all. You know, for these mesh regions, which I'm going to come to in a minute, it sort of breaks down to these simple cases anyway. So I've told you a lot about how you can use regions. They work in solvers. There are lots of standard properties that you can make use of. You can compute its measure, its location, membership tests. All of these things are standard, works with everything. Everything that I'm going to call a region, that works. So the basic regions or special regions are things that are primitives, okay? So we can have 1D embedded regions. They're not the most exciting, but they're there. And it's weird to not have them. 2D embedded, so here are some of the new ones. We have these infinite objects now, also works in graphics. So you can have a half line or array, an infinite line. Triangle became one because we had all these other special triangles. So these are triangles for these are primitives for solving things, you know, that you probably encountered in high school, which is where the request came from. You know, in this case, you know, side, side, side triangle. So if you know the three sides, what is the triangle? But they work just as any other region, and so on. So you'll see that there are quite a few new ones. Similarly, in 3D, some of the things we recognize, half-line, infinite line, but also half-plane, infinite plane, and something that looks a little mysterious, which is a conic hole, but it's a type of a hole, a cone, but piecewise linear cone. Some of the simpler polyhedra needed in order for mesh generation and other things. And quite a few of these generalize to n dimensions. So there you can use parameters that make them go to n dimensions. Okay. Now, then there's another big group of regions which I call formula regions, and there are two basic kinds. There's this one, which if you've used Mathematica before with region plot and other things, you're really familiar with already, which is that, you know, any list of conditions, basically, a Boolean or logical combination of conditions can define a region. And this obviously works in any number of dimensions. But here, for instance, is an ellipse curve. It's just defined by an equation like that. And we can use it. Point is that we can use it just like any other region. So as a hello world example, I often use integrate because it gives a short output for the most part. So you see more integrates than you probably need, but because it's sort of the hello world example. Here's an example of an implicit region, which is given by a combination of two things. So these are the annulus, and then I give it a half space condition. So these are very flexible and can give you very precise, definitions. One thing that I'm going to start introducing is that a region doesn't have to have one dimension all over the place. Think of graphics. We often have curves, and we have some polygon, and we might have some points. So it's all kinds of mixed dimensions. So regions in Mathematica can have mixed dimensions. Its actual geometric dimension is the maximal one, though. So this is a perfectly good region, which, again, we can integrate over and whatnot. And we can optimize over it. Did I actually? Oh, I forgot to define it. That works in any number of dimensions. Another type of formula region is where we can give a set of parametric functions, like parametric plot and parametric plot 3D. But this defines the mathematical object, the region. And again, it works in any number of dimensions. So the simplest example of that might be something like a circle, like an ellipse, since we've been using ellipses. So here defines a parametric region using parametric functions instead. And let's do the hello world kind of example. And you can see that you can directly use it, like in all the ways that I talked about. Now, so these formula regions are fairly general. Another very important general kind of region is what we call a mesh region. And the things that probably people are most used to seeing are things like this, where in 2D you have a bunch of triangles knitted together, or in 3D you have a bunch of tetrahedra knitted together. But mesh region needs to be able to represent what I just encountered on the previous slide, where we have mixed dimension kinds of things. Let's say that your geometry comes from graphics, then it needs to be able to represent that correctly. And so formally these are called cell complexes or simplicial complexes. But from the point of view in Mathematica, they work just like any other region. And the way that they're defined is kind of like graphics complex. You give a bunch of points and you give a bunch of cells. So if you've used graphics complex, you know how mesh region works. But it's now a geometric object, works in 1D, 2D, and 3D. Most of the time, you're not directly going to use that. Most of the time, it's going to be generated by other things. So a really common case is that you discretize graphics or discretize some other region. Or you use point sets to use, Delaunay triangulation of a point set. So here's a built from the ground up kind of region. So here's my list of points. There's my list of points, and here's my two cells, which are two triangles in this case. These guys, like graphs in Mathematica and like images in Mathematica, they automatically visualize themselves. But this is a perfectly good region. I can copy-paste it and use it like any other regions. All the other properties that we looked at, like dimension and measure and centroid and solvers and so on, work on this region, just like the other ones. Now here is a more common way probably to do it, is to use some other function that generates these. So one thing is this, to do a Delaunay mesh. So I give it a bunch of random points, and this one will compute it right away. But then this is now a geometric region that can be used just like any other region. Or we discretize some graphics. We take something that represents the same image as graphics and discretize it, like in this case here. And we can now, we could have, in this case, circle was already a region, so I don't need to. But let's say it's a complicated graphic you get from someone. You can discretize the whole scene. If you have many primitives, it's taken to be union. So it's basically the ink that you see when you see the picture would be the region. Okay, so everything I've shown up to now can be discretized and can be made into mesh region. There's a variant of this, which for many people is the only kind of mesh region that happens, which is kind of the generalization of polygon. So you know polygon, you just define the boundary curve and you say the polygon really means all the points that are inside that curve, that closed curve. So that can generalize to any number of dimension. If you have a closed surface, you can define all the points that are inside the closed surface. And that's exactly what boundary mesh region does. So often you need to specify a little bit less. The downside, it can only define full dimensional regions. So in 2D, it can only define two-dimensional regions. And in 3D, only three-dimensional regions. So no curves in 3D, for instance. But this is how much of the world, the things in the world are actually saved, okay? And it has a definition which is very similar to mesh regions. So you have a list of points, and then you give boundary curves or boundary surfaces. And as you saw in my illustrations out there, these can happily sort of include holes, which our polygon cannot, or voids. Am I in trouble, Cliff?
You're getting there, Roger.
Okay.
You got 1 minute.
Okay, so give me 2 and I'll be able to wrap.
I'll give you 2.
Okay. So, just like these other ones, you can define them from the ground up, which you probably do in an application, or more commonly, they're generated by other ones. So for instance, the convex hull from a set of points will give you a boundary mesh region. But then you can use the boundary mesh region in all the ways that I've talked about before. You can integrate over it, optimize over it, whatever you want to make it do backflips, scale it, transform it, you do it. Okay. Derived regions, final group, which is you take all the things I've said up to now, so you can tell that it's a recursive definition of what a region is. And then you combine them in some ways. So like Boolean operations is the probably quintessential way to derive new regions from old. Or you transform them with some function. So those are 2 really common examples. So here are Boolean combinations of regions, as you might expect, or transformations of regions, just number of transformations. Or here's another one, and there's many more of these coming. So I define a 1D region called a Cantor set or Cantor line. But then I can take the Cartesian product of these. So that's another way of deriving new region. Just take the Cartesian product of regions. So if I take the Cartesian product of these, I get a new one. If I take one more product, I get, and you can keep going like that. But that summarizes an overview. And as I said, tomorrow morning there's another one. This is a little bit too short, but it just gives you the buzzwords and the pictures. How do you learn? Well, I think that the documentation is actually quite excellent in this area. And there's a geometric computation. It even has a front tile on the new help system in Mathematica, which points to this, which is called the overview. And if you see what the topics I covered, properties and measures, these are the standard properties we talked about. Solvers, we talked about those. The special or basic regions, formula regions, mesh regions, and derived regions, which is kind of like the topics of the whole talk. So at least you got the buzzwords. So, thank you.